Just understand that if you have questions, please ask, because as we go through and work on this, it is going to kind of continue forward into later parts of the class. So with this material, please ask questions as they come up, because again, some of these topics that we're talking about now, so basically over the next 2.5 weeks, we're going to learn a lot of different analysis tools for going through and talking about circuits. So instead of having to hand do it the way we've been doing it, what are some techniques we can get around to use this with? We'll take a pause, we'll introduce new circuit components, and then we'll come back to these again. So they'll come back. So please, if you have questions, now's the best time to ask. That way you're not trying to do two things at once when we get into RC or RL or RLC circuits. So last time we talked about converting between our current and voltage source. So for that, when we had our voltage source, that was our situation where you had something like this, and we can convert back to forth between having something a little bit more like this. All right, so we can just flip back and forth between these, and that we can go through and we can utilize Ohm's law. So VS is equal to IS RS. So this resistor is the same for both sources. It's the internal resistance of whatever it is that we have. And we can just convert back and forth using Ohm's law. So we're not going to explicitly, we're going to see this if we get the third thing we're supposed to talk about today. We'll see this come back. But like I said, I don't think we're going to quite get there today. But so we'll see this again. But Ohm's law, just flip between parallel and series, depending on which source you have. Any questions from last time? So, like I said, don't think it's okay if we don't finish. I know it only looks like 3 sections, but they are 3 kind of beefy sections for this. We're going to talk about superposition, Thevian's and Norton's theorems. So this here is a lot of words to try to explain what superposition is. And so I just kind of want to talk through it. This is the circuit definition, so we'll go through, we'll talk about it. But in general, superposition is a way to take anything, look at it in different parts, and then combine it together into a total result. In particular, for superposition, for our circuits, what we have is the current or voltage of any given branch. So that is just a part of a circuit after a junction of multiple source linear circuits can be found by determining the current or voltage in that particular branch produced by each source individually. So basically what we'll do is we will look at one source at a time, whether that's a current source or a voltage source, one at a time. Once we have that one at a time, we can go through and find our current or our voltage across our particular resistor. In this case is typically what we're going to look at. Once we have all the values, we go through and add them together. That is what this superposition theorem is for circuits. So one source at a time, what is the current or the voltage across this resistor? Do it for all of them. And there are certain ways that we have to do this such that we make sure that we're accurately explaining it. Something we need to understand about superposition, as well as the 2 theorems that we're going to talk about today, is that these are mathematical constructs. We are not physically taking our circuit and making new circuits out of it. We're saying, if I took this one component out, what happens? If I take this component out, what happens? If I take this, what happens? We have to do that in a very specific way in order for it to match the same. But again, not something you're physically doing. is mathematically what you're going through and doing to pull this out. So there are 4 steps for superposition. First, you're going to have your circuit. In the case of superposition, you're always going to have multiple sources in some way, shape, or form. And what you're going to do is you're going to decide which source do you want to start with, and then you're going to take out all other sources. So for an ideal source, a short represents a zero internal resistance, and an open represents infinite internal resistance. So what this means is that what we're going to do is when we have a battery and we go through and we take it out, we are going to replace it with a line of wire. So we're going to replace it with a short, so there's no resistance here. So that means that it will change the flow, or again, theoretically, change the flow of how current will flow. For a current source, what we are going to do is we are going to replace it, and we're going to actually take it out and not replace it with anything. So it is going to be an open location. In order for current to flow, we have to have a closed loop. So basically what we are doing with our current source is when we take it out, that branch no longer has current flowing through it. Infinite current, when we replace a battery with its wire, or it's not technically infinite, but there's no resistance, so all current can flow through it. When we replace the current source, it's going to be open. So basically what you're gonna do is when you're going through doing this, you're gonna do this one at a time. So you'll have to do this for every single source that you have. So if you have 3, you'll have 3 new circuits that you need to analyze. If you have 2, you have 2, and so forth. So you're gonna just keep repeating this over and over and over again. So if you have 3, you'll have 3 separate circuits you need to analyze, go through, and have those. If you have 4, you would need 4, and so forth. Once you have them all, you just add the values together for whatever it is you're looking for. So in this class, we'll look at current or voltage. So either add all the current values together or add all the voltage values together. So this is superposition as a whole. We will see some examples for this in a second, but I know right now this is just a lot that is coming at you. Are there any questions so far? So we're going to look at this situation here. This looks probably a little, this isn't obviously the same question as the example. This is relatively similar to what you have. So when you guys did it on the exam and on the previous packet, right, this was kind of a pain to go through and do. Wasn't very fun. This is another method to go through and utilize it. So what we have here, right, is we have 2 different sources. So here we see that we have VS1 and 2. We do need to make sure that we understand that they are different. We have 2 resistors, right? So the current's going to go through that. It's going to come together. It's going to flow through this middle resistor R2 here, and then go back around. In this particular question, it is being asked for us to solve for I2. So what is the current of the 2 of them coming together? So if we think about the skills that we had before, we would need to go through and utilize the loop or the voltage law. So that one would be going through and looking at the change in voltage as we go around 2 of our loops. And we would need to use the current law to look at the current coming into one of our junctions or in and out of one of our junctions and go through and solve a system of 3 equations. With superposition, it's going to be a little bit different. So what we would first need to go through and do is decide, do I want to start with analyzing with the left battery or the right battery? So this textbook is started by doing the left battery. So what we're gonna do is we're gonna say that's, okay, so I only care right now about this left battery here. So what I'm gonna do is I'm gonna take out the right battery. I'm gonna pull it out of my circuit and I replace it with a short or an ideal wire. So batteries get replaced by with an ideal wire. So now I have a new circuit that I can go through and analyze. So with this, I now have a way to go through and explain the relationship between R3 and R2. What are they now? Now they're in parallel. And then if we combine that, it's in series with R1. We have done this before, where we can go through and we can now find the current through R2. Okay, so we can find the total current that comes from this battery. All of it passes through R1. We can use whatever technique that we like to find the current through. We just care in this case about R2. So that is what these steps here are. So here we're finding our total resistance. So 2 and 3 are in parallel. R1 here is in series with that. Find the total current that's coming out of this left battery. You'll see that when we see a short or this new replaced ideal wire in the textbook, it's gonna make sure that it's marked a little bit separate. If you just draw it as a straight line, that is perfectly fine with me. I'm not gonna care. But just understand the textbook is gonna say that this is a separate little piece of wire. It's the same as the rest of the wire. It's just, this is a special thing where we've replaced a battery. So it's just a notation thing that this textbook's gonna do. You don't have to do it. So we could go through and we can find the current through 2 utilizing this equation here. So this is the current divider current divider equation. So this is the current that's going to flow through the middle. Again, same method that we first learned in this class. We're just applying it here for the left battery. Any questions about what we're doing with just the left battery? So we then do the exact opposite. I'm going to now go back to my original circuit. I've now analyzed what I need from this left battery here. Now I need to go through and do the right battery. So now I'm going to take out the left battery and leave in the right battery, and I'm going to do the same general steps. So here I've replaced my battery once again with an ideal wire. Now, if I look at it, R1 and R2 are in parallel. Whereas before with that second battery, they were not. And I can do the same general process. Go through, find the total resistance. That'll have me go through and find the total current. I can then find the current that is flowing through R2 here from the right battery. So in this case, we would be done looking at the different sources. Right? I only have 2. I've done my analysis twice. I'm at the point now where I can take my 2 circuits or my 2 results and add them together to find the value of the current flowing through the middle. So before we talk about that, are there any questions on dealing with the right side battery? Yes.
I guess for both sides.
Yeah.
Where does that equation come from for the G and E? Or,
This one?
yeah,
So this is your current divider equation. So it's just, instead of going through, so you have the total current coming in, it splits based off of your resistors here. And so it's,
There were total resistance over.
it is, so it should be the total over, but if you go through and do the algebra, that's what we would have is if we wanted to look at the, total value for the, parallel. Right, so let's just do this for, the left one. The same equation works out for the right one as well. Our, RT in this case is the total value for the parallel, so that's 1 over R2 plus 1 over R3 to the -1. And then we would have, in this case, Rx would be equal to R2. If we go through and do this at the same time, algebraically, it's gonna pop out to this. So that's where it's coming from. Is it saying, instead of plugging in for this number and plugging in for this number, we could go through and rearrange it to that. Yes,
So in this scenario, though, getting the superposition, we could simply go by the electron current, and then we would add the voltages together if we knew the voltages. And then go through the circuit. And we should get the same values, right?
typically we will know let's hold off on that and see if his question's done first. And while we check that, I am thinking about your answer. So does this kind of answer,
I don't get it, the probably answers.
maybe we could. So what we would have, so for, right, for IX, it would be equal to RT. Over R2 IT. And so I don't know about you, but this is algebraically unhappy for me.
Should you add R1 though?
In this case, no, because all of the current flows through R1
Okay,
and then it splits here between 2 and 3,
okay,
which is why we don't need to include it
even for the total.
here. It is useful for it's used for finding the total current. But when we have it split at the junction, we cannot include R1 because it's not part of the split of the current. Yeah, so then this algebraically comes out to that.
Okay.
All right, so let me see if I understand your question before I answer it. So you're saying that if we did the electron current instead, so looking at this way, if we knew the voltages, we could just do it from there.
Yeah, because when well, in this case, let's say VS1 is 12 volts and then VS2 is 24 volts. When we get 12 volts, that would be going through R2 and then,
In this exact case, probably technically don't need superposition. This is probably the single nicest case you can have for this. So it would work in that way. When we start getting more complicated circuits, we cannot. But in this case, if we knew all the voltage values, it might be easier to go through and do it a different method. Just depends on what you're more comfortable with at the end of the day. So this one, probably not the best. You have to use superposition example. Especially since I showed you guys how to do it. Any other questions before we do the superposition portion of it? So all we would need to go through and do at the very end here is just add the two currents together. So we're going to take current from the source on the left, take the value from the source on the right, add those together, and that will be the total current that flows through this source. So this is the general procedure for superposition. Look at each source individually, replace your batteries with an ideal wire, replace your current source with a open circuit, so you're actually breaking your circuit. go through and see if you can find the voltage or the current across that missing piece. Any questions about superposition so far? So we're gonna work through 12A together. So with this, we need to decide which one we want to look at first. So we'll do this by vote. The option will be we'll call it right versus up. Who wants to do the right source first? Who wants to do the up source first? Okay, we'll do the up source first. So what I'm going to do here is the first thing we're going to do is we're going to leave the up source. We're going to take out the source that's pointing to the right. So we're going to redraw our circuit. The best of our abilities. For this one that we're taking out, we're going to leave it with a break in the circuit. It's going to look like this. This is right here. So this is now what we have. So we are looking at the situation where we have this 2 amp source. Now we will have to look at the 1 amp source after this. So if we go through here, right, we want to find the load current in each circuit. So in this case, our load circuit is the one with RL here. So with this, for the current, let's explore what happens as we go through and do this. So if I'm starting here, I come up, I come to this junction, I can go left down to this resistor, back to this junction and through. My other option would be coming up and going to the right, but there's nowhere for the current to flow. So it cannot go to the right here. Which means that there's no current coming in to this bottom portion here, which means that the current through our load here must be equal to 0. By having this break, we are saying that this up pointing current source does not contribute to any current flowing through RL. Questions? So now we want to do the other situation where we're going to take out the up pointing one, and we're just going to look at the one to the right. Again, we go through and we redraw our circuit. We have a situation like this. So with this here, again, let's go through and let's look at what the current is doing in order to go through and figure out what we need to do. So it's going to come out, it's going to go to the right, it reaches our first junction, and it's going to split. So some of it's going to go through our 2.2 kilo ohm resistor, and some of it is going to go through the 3.9 kilo ohm resistor. It's then going to come back, and it's going to combine, and all of the current is going to flow through the 10 kilo ohm resistor. So that's what's happening here with the current. So what I need to do is I need to figure out how much of that current is flowing through my RL, or the 3.9 kilo ohm resistor. So with that, we need to think about how to go through and do it. Before we do, are there any questions so far? So in this case, do we know the total current that is coming from this source?
Yes.
What is it?
1.
So in this case, IT is equal to 1 amp. So we don't need to actually go through and solve for that. That is what is being supplied by the current source. So we don't have to solve for that. That means we can just go straight through and we can use our current divider equation. So if we recall for that equation, we have IX is equal to RT over RX times IT. We're kind of come back to this in a second. If you look at all examples in the textbook and how it's gonna go through and do it, it is always going to start with something that looks like this. It is always gonna go through and it's gonna have the simplified version for going through and doing it. So the textbook is gonna move on to here, moving forward with how it does its current divider. You don't have to if you don't want to. I'm just letting you know, that is where the textbook is gonna be using. So if we go through and do this here, right, we want I through the, when we're doing this, it's not super clear in the question, it expects you to understand. So it says find the load current. That means that we need to look for the resistor with the subscript L associated with it, which is gonna be the far right one here. So what I want you to do is decide on if you want to use this equation, or in this case, let's just call this one R here. If we use R over RX, or sorry, RL plus R. So decide which one of these you want to go through and use, plug it into your equation and see what you end up getting for your current. And remembering here for RT, for the current divider part, we only want these two here for RT. Because those are the two that are in parallel. This one is different because it has all the current flowing through it. Go ahead and compare your answers with your neighbor. So before we talk about answers, do we need to convert our kilo ohms to ohms? Why or why not?
That's which one we're doing.
Yeah, in this case, it doesn't matter. We don't have to. The reason for that is gonna be as we have resistance divided by resistance. So if we do the conversion, our conversion is gonna end up canceling out. So we don't technically have to convert here if we don't want to. It does not hurt you to convert. We'll see in a later example that you do have to convert one of the, one way or the other. If all of the resistors are given in the same situation or the same prefix, it doesn't really matter if you're dividing. If you were to go through and do some multiplication or something, that might be a different case, but here we have resistance divided by resistance, so we do not have to. Would somebody like to volunteer what they have for the total, with a couple extra sig figs, the current they got, and which method that they used?
I checked both, but I got 0.3607 amps.
Let's do one extra sig fig, so let's do
6.6, yeah.
amps. So, and you did both methods and got the same value? So, again, the textbook's gonna show us this one because it's this, but just rearrange. You are more than welcome to do this. I don't care. Personally, I do it this way. Cause I don't know, every once in a while I try to do it the other way and I always what I end up doing is I always use the wrong resistance value by itself. So I personally have to do it the long way. There's nothing wrong with that. So this is, let's call this IL, right? This one is IL up. To find the total current, we need to go through and add these two values together. One of them is very kindly a zero value, so it's not very difficult to do so. So this means that the current through the load will be 0.361 amps or 361 milliamps if you felt the need to convert it to a prefix. Yes.
If we were to have something with it splitting off more, or like,
If you had three, yeah.
what would it just be easier to do it the normal way?
I mean, I always think it's easier to do it the normal way, so maybe don't ask me that question. The textbook for one of the methods we're gonna look at a little bit later does have more. And so, but it will always go through and have the simplified version. But it is 100% up to you on what you use. Any questions about 12A? Well, what I want you to go through and do, you feel free to work with your neighbors while you do this, is I want you to draw the 3 circuits you need for 12B.
Well,
12B.
oh, I thought we were talking about 12 volts, not in Bravo.
No, B for like bumblebee.
We have a tracker for this.
I'm not done with it yet because if I'm being honest, this is like my single least favorite subject that we're gonna cover in this class. So I'm struggling to actually make a packet that isn't, spiteful. And not like spiteful hard, just like spiteful, like in this method. Like. I think superposition is fine. It's the other 2 theorems that we're supposed to talk about that I have some beef with.
Interior resistance, no. I mean,
To assume it's infinite.
oh, yeah,
I don't even know where to start.
Right? We just did it for 2, now we just got 3.
it's fun. Better not to do this way. So, just like some hidden pockets, some features.
No, it's not very fun. Plus. All right, so what do you, if you were to replace a battery, what do you replace it with?
Battery.
We take out, we replace it with either an ideal wire or an open. So what we do is switch over and
The current source you would open with the battery, ideal wire.
So what you're gonna do, since you're starting with this one here, is you now need to go through and for all your other batteries. Replace it for ideals. And for all of your current sources, replace it with open space.
One current source.
Yes.
See, you can say where it's there's not.
Yeah, it doesn't take very. So now we stop this, that is one of your,
Let's see a little bit of thing.
yeah, just make sure you have all your
Surface
sources.
matter.
So you have one of those, and now you need to draw your two other ones. So now, because you've done this one, now you need to go to the current source and the baby
Presentation.
So you have three
What's
circuits.
happening? Sure, presentation.
It's not for you, it's for someone else.
Except for the fact that we're not showing it numbers, so it's for duty now for future.
What did she say?
The most electrical stuff that could possibly done in my current job is studying DNA science. That's chemical circuits. I'm secure.
I think the graph teachers are really helping math here.
Yeah. It's like amazing, especially when I do my other homework, so I can just trace it.
Yeah, I feel like your circuit looks a little bit neater
Okay.
than some others. Not everybody's picking up. Mine are gonna be pretty rough moving forward with this.
Yeah.
You need statistics.
Alright, does anybody need more time for drawing their three circuits?
No, I just finished.
Alright. So let's go through and let's just do this from left to right for going through and doing it. So I'm gonna start with my left battery here. I don't ever change the resistors with superposition. So what am I gonna do here for my current source?
So.
I'm just gonna leave it open. Right, current sources, we just pull out. And then need to redraw the rest here. What do I do with my battery?
Circles.
So we're replacing it with an ideal wire, which the textbook is gonna refer to as a short. You can draw it this way if you want to, or you can draw it as a straight line. Like I said, I don't care. And then we're gonna go through and we're gonna draw the last little bit here. In this case, the marks for A and B are not 100% useful. In this case, we're still looking for the value across RL here. A and B tell us the same thing as the current or the voltage across RL. So we can just focus on RL. We don't need to worry about drawing A and B into our circuit here. Any questions on this one? Okay, so we need to go through and we need to draw our two other ones. So we're just gonna replace, in this case, I'm gonna go through and I'm gonna look at my current source. So here I'm just gonna draw them as straight lines instead. Again, it doesn't matter which method you go through to use. So for this one here, right, I've replaced both of my batteries with an ideal wire, so they're straight lines. Again, I don't care if you draw the circles, the textbook will. I'm not gonna be here to harass you about that. So that's our second one. And our third one. Something like this. Okay, so these are the three circuits we need to now go through and analyze. And in this case, we are solving for current. So that means that when we go through and do this, we need to focus on the current and what's going on in RL. So I'm going to look at all of these here. So let's go ahead and let's focus on our first situation here, which corresponds to the left battery. And so with this, I'm going to start here at my positive. I'm going to go down. I'm going to go through a resistor. No current flows up because it's incomplete here, so nothing interesting happens. I get to this junction here, and which path has the least resistance? Yeah, this one has no resistance, so what's going to happen is all of the current is going to flow up through this wire here. So for all of the current for this left battery, it's going to go through like this. So that means RL is going to be equal to 0 for this particular case. Questions about the left battery? So if we look at the, right, our current source, we have two things that can happen. It comes up, some of it can go around this way. Sorry, my lines aren't connecting. It is actually connected. I will fix that here. Right, so it has, there's nothing wrong with the current, let's see, flowing around to the left. This is a complete loop. It will have some current. If I look at the other way, right, it's gonna come through this here. It's gonna reach this junction. And again, there's a 0 resistance path. It's gonna take that. So all of it's gonna come through and down here. And once again, I will have a situation where RL is equal to 0. We have this path or this path, we have another 0. So for two of the three sources, they do not contribute through a current through RL here. So the only one, when we go through and add everything together, adding 2 zeros, the only one I actively am going to care about is this right battery here. So let's look at the two situations that it has, right? Some of the current is going to come out through here, and some of it is going to come through and do the other loop. So with this here, right there again, multiple ways we can technically go through and solve this. So we just need to go through and decide. Do we know the total current coming from this battery?
Yeah.
Not yet. That's the first thing we got to go through and do. So with this here, what do we know about our 1 kilo ohm and 1 kilo ohm?
There else need to.
Oh, oops. The 8.2 kilo ohm. What do we know about these three resistors?
Series.
They're in series. What do we know about the 560 ohm resistor and the 1.5 kilo ohm resistor of RL?
Series.
They're also in series. What do we then have for them together? They're in parallel. So we can go through and we can find that total resistance value and solve for it, and then solve for the current. Or what we can go through and do is we can use the voltage divider to figure out how much voltage is across a branch. Because we know that for this here, if this is 60 volts, this part has to be 60 and this part has to be 60 as well. So we can use our voltage divider to go through and say, well, hey, this is the voltage across RL. And once we have that, use Ohm's law to solve for the current. So both methods work out. Just depends on what you're more comfortable with doing. So. You guys want to see it with the voltage divider? Or do you want to see it the other way that I don't think technically has a name? Both. So let's do it with the voltage divider. So for our voltage divider equation, Vx is equal to Rx over RT Vs. So in this case here, when we're using RT, we only need to care about the two that are in series with each other. So that means that the voltage across L is going to be equal to RL over, let's just call this R here, R plus RL Vs. Do I need to worry about converting here?
Yes.
Yes. In this case, because I have my volts or my voltage given in volts, it is beneficial to go through here and have everything in ohms as opposed to having everything in kilo ohms. Because if I go through and plug it into kilo ohms, what I'm gonna have is it's gonna pop out in millivolts. Not
Millivolts.
sorry, it'll be in kilovolts, but we're not gonna have a whole kilovolt because we only have 60 volts going into it. So it's beneficial to just go through and have it all in ohms. So what we'll have is we'll have 1,500 ohms over 560 ohms plus 1,500 ohms times 60 volts. Taking this and plugging it in, I got 43.689 volts. So this is the voltage drop across RL here. And now that we have this, I know the resistance, I know the voltage drop. How can I find current?
Ohm's law.
Ohm's law. IL is going to be equal to VL over RL. So I'll use my 43.689 volts. Here, again, I need to make sure that so my current pops out in amps, I am using ohms. I'm going to have my 1,500 ohms. Taking this and plugging it in, I got 0.029126 amps. So for rounding, my current through, again, because I have two other zeros, I need to make sure if I had more, so if I had a non-zero value in one of these, I would need to add. In this case, they are both zero, so I don't have to worry about it. So I'm gonna go, I can just round this here. I'm gonna have 0.0291 amps or 29.1 milliamps. Any questions on 12B? Yes.
We had the internal resistance of the current source. Could we do this a different method too?
Yes, but we need a different, superposition tends not to be the method you would want to go through and do that with.
Yeah.
Like
Just kind of, yeah, use this method.
yes.
But you wouldn't be able to do anything else if you did have the internal resistance of it.
So here,
Would you need to convert it all into it?
typically, if you had internal resistance for one of your sources, one of the things that you can do is convert them all to the same type of source and then go through a new superposition. With the two other methods we're gonna talk about, they have ways of getting around that as well. So you might not want superposition explicitly for one of those.
Okay.
So. Any questions about superposition? All right. This is one of the two major theorems. This is a way to not use superposition for it. And so this is okay, I'm gonna be 100% honest. I don't know if this is the correct pronunciation. This is how my professor now did it. I don't know if it's correct. Bevian's theorem. Again, don't know if that's correct or not. That's just how I learned it. So it is the equivalent form of any two terminal resistive circuits. And it consists of an equivalent voltage source, VTH, and an equivalent resistance, RTH. So here we need to indicate that these are TH because of the method we're going to go through to use and solve. We're also going to, in theory, we'll get to Norton's theorem. Those will have the subscript of N. They are very related to each other. We're going to spend some more time going through this theorem here. Most textbooks will do this theorem first. So spend an extra little bit of time on it. And then when we get to Norton's, we'll just kind of talk about how they're different in that regard. So when we are doing this, again, it is a mathematical representation. What we are going to be going through and doing is we are going to be taking our circuit and we are going to be completely redo it, or not completely, but we're going to heavily redo our circuit to look like something else to go through and solve. And so again, this is a more mathematical model thing, not something you would physically go through and do with your circuit. Because if you did, you're probably breaking a bunch of stuff in the meantime. So with your voltage, your equivalent voltage source and your equivalent resistance, these are going to depend on your original circuit, whatever that happens to be. So, right, different circuits, different equivalents. So the equivalent voltage is the open circuit or no load voltage between two output terminals in a circuit. So with that, what we will be seeing is we are going to be going through and instead of looking at the resistance across a load, you basically just rip it out and replace it with a voltmeter. Essentially what we go through and do. So that is the open circuit part. So we're going to remove a resistor. We're going to put a voltmeter in its place to go through and look at the voltage. So in this, right, a voltmeter measures voltage. So in this class, the symbol that we're going to be using to do this replacement is the V inside of a circle. So you will see this used, it was, do this the other way. We had our load resistor, that is going to become BL in our circuits. So it's just some way to read the voltage, and it is replacing the load resistor. The equivalent resistance is the total resistance appearing between two terminals in a given circuit, with all sources replaced by their internal resistance. So you wanted to know what happened with the internal resistance? Here it is. So if our sources have internal resistance, we are going to remove them and replace them with a resistor that corresponds to their internal resistance. This is a lot of formal definitions. We're going to see an example, just a kind of breakdown circuit example here in a second. Any questions so far?
So physically, when you draw that diagram, it's just gonna be the battery and then it's just gonna replace with the resistor symbol.
We have to keep one battery.
Okay.
Or sorry, no, yeah, we're gonna we will take our battery out for this method. If it has an internal resistance, it becomes a resistor. If it is an ideal source, it becomes a straight wire. Any other questions so far? We are making a whole new circuit with this. This can be, sometimes needs to be done in a lot of different steps. That's totally okay, and talk about it. But basically with this theorem, we are making a new equivalent circuit by essentially starting all over, image-wise. So understand we are making a new circuit. So what this kind of, and again, we'll look at an example here in a second, what this kind of equates to is we have some original circuit. Right now, we're just treating it like a black box. We don't know what it is and we don't really care at this instant in time. It has some output. So these output terminals is going to be where you're going through and doing your measurements. There is some amount of current coming into that load resistor. And there's some amount of voltage across it. With our new equivalent circuit, we need to have the same exact outputs. So we need to have the same current that would flow through the load resistor, and we need to have the same voltage across the load resistor. Everything else can be different. So that is what is happening. We need to, with this, for it being equivalent, has to have the same current and the same voltage across the load resistor. I don't care about any other resistor. Only the load resistor matters to me. That's the only current I care about. That is the only load I care about. Questions so far? So the awkward thing about it is it depends on how you are viewing your circuit. So here we just have, if we're being honest, the simplest circuit you'll see for this in the chapter. We have a source, we have resistor 1, and then we have resistor 2, resistor 3. And we can go through and we could look at, say, resistor 2 is the load versus resistor 3 is the load, or the resistance of 2 and 3 together is the load. So if we say resistor 2 is the load, that means that when I go through to measure the current and the voltage, I would need to look at between A and B here. If I wanted it to be resistor 3 to be the load, my voltage and current I need to care about those through BC. I care about the whole thing as the load, I would need to look at A through C. So depending on what we want is going to determine how we need to go through and approach this problem. In this textbook, for the questions that I will be assigning you, it's going to be one option. It's AB. So you would care about for AB, what is it that we're going to go through and look for? So here, this is for looking at it for A to C. So this is going through and saying AC, or sorry, resistor 2 and resistor 3 here are my load. So because these two are my load, I care about the voltage drop across resistor 2 and 3. And only resistor 2 and 3. So we can go through and we can calculate that value using a voltage divider. So again, with the voltage divider equation, we have Vx is equal to Rx over RT ds. Where here, I'm not caring, I want the voltage drop across 2. So in reality, Rx is gonna be both of these here. So resistor 2 and 3 are RX for the purpose of our voltage divider equation. Again, this is if we want our load to represent both of these resistors. If we want it instead to just be one of the resistors, again, we would need to go through and use our voltage divider. And here, this is just saying that R3 here is equal to the load resistor. So in a circuit, you would see it as RL instead of R3, if that's what you wanted to go through and look for. So then these two together here are RL. So depending on, again, questions you'll see in this textbook, you're not going to have to worry about this or that. There'll be one option. So it would be more akin to what we have in the second example here, which just across one resistor. When we have that resistor is going to be identified as RL. So RL is going to be the one that we want to look at for the current through it or the voltage across it. It's the only one we're going to care about. Questions so far?
A, B, and C are places where you can read the voltage.
Yes. So if you did A to B, you attached your voltmeter to it, it would read it's in parallel. So it now would have the same voltage as resistor 2. Same thing with C. Any other questions so far? So let's talk about the steps for solving this. So basically what we're going to do is we are going to open the two terminals. So what that means is you'll have A and B on your circuit. There will be something between it. You are literally going to take that out. So again, that's going to be our resistance, our load resistor. So the RL, we're going to take that out. We then are going to determine the voltage across those two terminals. So we, in the circuit, replace it with a voltmeter. So that's going to be the VL that we have. So in the diagram, it'll say VL, the voltage value is VTH. You then need to determine the resistance. So this is RTH between the two open terminals with all sources replaced with their internal resistance. So if it has some internal resistance, the battery becomes a resistor. If there is no resistance for the battery, it becomes an ideal wire. So that is what this is kind of saying here is. Right, so we are placed with internal resistance. This is really dark, sorry. Right, placed with internal resistance. Ideal is a short, current is opened. So 3 things we can now do. Replace with a resistor, replace with an ideal wire, or replace by just literally pulling it out and not replacing it with anything at all. So replacing with an open. Once we do this, that's going to help us go through and figure out the resistance. I heavily recommend redrawing the circuit before you find this resistance value. Because when we do these replacements, what was in series and parallel might change. Connect VTH and RTH in series to produce the complete equivalent for the original circuit. So basically everything should boil down to one battery, one resistor, and a voltmeter. Once we have that, we are done. So, or I guess we're not technically done. It says replace the load removed. So now you just take the voltmeter out, put the resistor back in for picture purposes. So we are gonna work through an example here, but before we do that, are there any questions? I'm gonna keep flipping back and forth between this slide and the problem we're working on. So, oh, sorry. Real quick, we're gonna talk about this, then we'll do the example. We'll spend a little bit more time on this, after we talk about the Norton method. With it, this is one of the ways we can go through and solve the Wheatstone bridge. Yes.
I was trying to think what my question was, but, so for like an internal resistance, and you were saying that when we change a battery.
We replace a
Or
battery or a current source with an internal resistance. We just replace them with that. So the resistor replaces, sorry, the internal resistance replaces the source.
But that, so that'd be given,
That would have to be given.
okay?
Otherwise, we will assume it's ideal. So, Wheatstone bridges are a really good place to go through and use this method. So what you can do is you can take out the load, that's typically the one in the middle. Redraw it. So this is, again, when we talked about Wheatstone bridges a week ago. Right, we said that these two were equivalent. This is helpful for going through and doing our replacement here. So with it, what we would need to go through and do is look at the difference in voltage across the two sides. So here we have VA, so this is the voltage at A. So this is associated with the resistance drop across R1. Or sorry, the voltage drop across R1 minus VB, so the resistance drop across R3 here. And once you have this, you go through and you redraw it. So here we're getting rid of the battery and replacing it with an ideal wire. And so this is going to change how we would go through and view these resistors. Because now, if we're looking at it, I don't have a circuit component between where R4 and R2 come together and when it goes to R2 and R3. So the tool for this particular method is getting rid of our sources. And by getting rid of our sources, that is changing the behaviors between series and parallel. So, so I'll talk about these in a second. So with this method here, we can go through and we can draw this diamond with 5 resistors to be this here. So these two are equivalent to each other. So this combination of resistors is our equivalent resistance value. So now we have R1 and R2 in parallel, and R3 and R4 are in parallel. The combination of the two of these is now in series. The voltage drop matches what it used to be before. So with this method here, this is really one of the places you can go through and derive the equations we just used before. It comes from this. That was the grand point of this slide here.
How is
Yeah.
R1 and R2 in parallel?
They're only in parallel when we start going through and creating our equivalent circuit. They're not in parallel in the form of the Wheatstone bridge. So we are making the equivalent values. So we're getting rid of this middle one here. We're also getting rid of our battery to an ideal wire. That makes it such that R1 and R2 are gonna be in. Here, sorry, I'm trying to remember. How to. This is why I don't like this method, is. I don't think it's clear going from here to here to this. I don't disagree. But what it's saying is, so for this here. If we can redraw this, I'm gonna have to draw it on the board because I don't have space here. And we'll put this in the slide. So if we just focus on R1 and R2 here with what's given in the picture. They have the same junction here. And so they have the same starting and ending point. Like this. So this here is redrawn. As this. But how you're supposed to know how to do that, this textbook doesn't show you. I don't know. Yeah, so it's saying that these two are connected like this. And then if we wanted to look at the other two. They have this junction and this junction, so then it becomes. This here. So because they share a junction between them, that's the end point. And then they have the same starting point, which is where the battery used to be. So that's where this image here is coming from. I don't intend on making you do this. Again, the Wheatstone bridge is something that's nice for determining a resistance value. It's also useful for going through and displaying all the different models. But they all give you the same exact results, so I'm okay just using straight up the results, regardless of model. Any questions before we just look at, we're not gonna get to the example, that's perfectly fine. Any questions on this method just in general so far? So what we'll start with, next time we'll talk about the steps again, and we'll go through and look at 18 here. We're just gonna do A and B, C and D are gonna be on the homework. So with this here, we're gonna go through and we're gonna take the steps of going through and drawing out the new circuit. Again, the equivalent circuit and the original circuit will look different. All right, so we're gonna have to take out our battery and we're gonna have to take out our L here. So I just want to briefly just talk about the image because this is typically gonna be what you see for both this method and the Norton method. And so with that, A and B are going to be clearly identified. They're always going to be associated with where our L is. So basically you're going to have A in the direction of current first and then B afterwards. So when you take out the load resistor, that's going to be where you could go through and replace it with that volt. But like I said, this is where we start on Thursday. So for tomorrow, have your packet done for this chapter here. So it'll be all of chapter 8. I just need to go through and make sure that I'm not overly sarcastic and mean about some of the wording of these steps. So I need to just go through and do that. That'll be what we do tomorrow. And then we will continue on with that. Yes.
So for this example, the internal resistance should be zero. Ideal.
Yes, this is an ideal source. You'll see that a lot of these are going to be ideal sources. Any other general questions? So I will see you guys later. I'm listening, but I'm gonna, let me stop the video before I answer your question.
It's just so. So if it's like, not